right? So these are the basic characteristics of queues and the data structure. And let's look into the operation of the queues. Actually, what we have as a queue operations are two. One is in queue operation, and the other is the dequeue operation, right? So in queue is actually the insertion operation, and dequeue is actually the removal operation, right? So insert an instance, and because we voluntarily gave up the mid access, right? That's the virtue of the queue, right? So because we just voluntarily gave up the mid access, we always be able to insert an instance at the rest, and we always remove an instance at the first. So it means that we don't have to specify the index of these enqueue and dequeue operations, okay? So imagine this case. We are in the airport and we lined up this me, that's me, and this prop Shin, and this is prop Li. Let's imagine that we lined up this way. And what actually happened was like enqueue Li, right, like this, and the enqueue Shin, so that's the first element, and this is second element, right, and then first element, and second element, and third element. If you recall the stack case, this first, second, and third will keep changing when we like pushed an item, right? Push and pop. Do you remember of the operations of these stacks, right? When you push a certain item, the index always changes. Here, in this case, enqueue doesn't change, change anything, right? But however, the dequeue changes actually the index, and the prop Shin becomes the first element after dequeuing Li, and Mi becomes second element, right? And I'm going to be the first element after dequeuing Shin. So that's how it operates, and this all illustrate the FIFO operation, right? And FIFO operation is only enabled by giving up the mid access point, no mid access point, and the operations are only the enqueue and dequeues are allowed, okay? So after dequeuing moon, then there will be none. Okay, how to implement this queue? How to implement works like this. So imagine this, we have this, actually it should be association relationship, and I really need to change, because that we have this RST instance as a singly linked list as a property, means that this one queue has just one list instance. So means this becomes much clearer, right? And that is the association relationship, right? And so we have this constructor to set up a default value and initialization, and we have this dequeue and enqueue case, and we have this dequeue, and always removal happens at the front, right? In stack we defined top, right? A special point top, right? The first element, and in queue case we have two special points, the front and the rear, right? So the front is the first element, so we remove at 1, right? So that's what happens. And enqueue always happens at the rear, at the rest, at the end of the list. And that's how we do it, right? Insert, add, and the get current size, and put it in the next of the current size. That's what is happening here, right? So this is the dequeue and enqueue operation. Again, if you have a complete singly linked list or any linked list, we this stack and the queue implementations becomes pretty easy, right? It's only about manipulating this linked list at a certain point, right, with a certain restriction. that's how stack and queue operates, and all the basics are in the linked list, right? So understanding and able to implement linked list is one of the keys, right? Right. So how about this? Actually, we talked about a little bit about circular linked list in the previous linked list lecture in week 3. At the end of the week 3, we talked about this in circular linked list. And circular linked list is like this, right? So we have head A, B, C, D, E, F, and what we don't have is tail. We omitted tail, and the last reference again next of the last node has to the head, and that was the difference. And how can we utilize this circular linked list for a queue implementation? How we do that? So actually how we do that is like this. So we have this circular linked list. Actually it is a good base list structure for implementing a queue. For an empty case of the circular linked list, it looks like this. We just have head, right? And after enqueuing Li, what happens is that we always put a certain item to the previous of the head, right? So what happens when we put an element previous to the head is that head points to the previous one becomes probably, right? And because there is no element, this previous elements, the previous one is actually head, so head next becomes this one, all right? So that's what happens when enqueuing Li. What's the benefit here? You see, in the previous implementation, we had to find out the size of the list, and in this case, when we enqueue Li, when we are enqueuing something, we need to get the size. But do we need size here? No need on list size info, right? That's one benefit of using circular linked list in the in implementing queue. So actually, we just can call the head previous, and head previous will be the last element, and that's where we are going to insert the node in the list, right? And that's the enqueue operation. If we are enqueuing Shin, then has prep changes to the Shin, and preps becomes the Professor preps becomes the Professor Li, and this is already has this direction, right? And enqueuing Moon doesn't require this information as well. We can just follow the head's previous, and we can just insert the node, right? So means that if we don't keep the track of the size of a list, whenever we call this size operation in the singly linked list, we have to go through the whole list to find out how many elements are there. That will take the n retrievers, right? And if we implement circular linked list, we don't need that list size. Then we don't have to keep track of the list size. One less information to implement. Means that if we become smart in using this linked list, then we can reduce the implementation size, right? So compared to using the doubly linked list, this circular linked list has a much benefit in implementing queue, right?